As promised, mathletes, here is part 2, Fluffy the Wonder Hamster push on a box with a force of 11 newtons. Will it move? Looks like they're letting the cat out of the bag, and there's a kinetic friction force of 6.27 on this case. So if that's true, that's bigger than that. Yeah, it'll move, not even move, but it's going to accelerate because 11, the pushing force, is bigger than the friction force. Now, if it's at rest, that's not the static force, though. So let's see what happens here. Well, I guess we found that a moment ago. They gave us an example. The maximum static was 10.6, if you remember. So they didn't have that hidden on here. So you have a difference in forces. This force forward is a little bigger than the maximum static. So yeah, you have a net force of 0.4 newtons to the right. So it is going to move. It's going to break loose. But the tricky thing is, as soon as it breaks loose, remember the friction is going to drop down to this 6.3-ish newtons down here. So now to find the acceleration of the box, so in other words, we already did experiment to find the kinetic was 6.27 all the time. We did experiment to find that it's 10.6 at a maximum. So you know if we push with 11 newtons, it is going to budge because we're above that. But as soon as it moves, that friction drops down to 6.3 because now it's kinetic. So to find the acceleration, we actually use the kinetic friction force, the 11 minus 6.3. That's 4.7 newtons. Well, guys, I know how much you guys love the FMA. So that's what's next. That's how you're going to find the acceleration is from this net force. 19.6 plus 19.6 down is 0. 11 forward plus 6.27 backwards is 4.7. Now you just find the acceleration. So it's your 4.73 using 2 sig figs, even though that's a 1 sig fig there. Oh well. And you end up with a 2.35 meters per second squared. All right, that's a little bit of a stretch because we got one too many sig figs, but well, we'll deal with it. Okay, so it gets faster by 2.35 meters per second every single second in that case. All righty. So the lesson on Monday then is how to find the stickiness of a surface by what's called the coefficient of friction. And we're talking about both the static coefficient of friction as well as the kinetic coefficient of friction. And what it is, it's a ratio of two forces. It's the fancy F divided by the capital non-fancy F. So it's your friction force divided by the normal force, which as long as you're on a flat level surface, that normal force will be the weight if you're on a flat level surface. And if nothing's pushing down on it or lifting up on it. So as long as the force is sideways, it won't make it seem heavier by pushing down into it or lighter by pulling up on it. So the normal force is not always the weight, but on a flat level surface and you're pulling perpendicular to the weight or parallel to the surface, it's going to be the friction force divided by the weight. All right? Because these are balanced when you're pushing this way. If you're pulling down, it's still balanced, but the normal force would increase. If you're pulling up, the normal force would decrease because you're kind of lifting up on it, making it seem lighter to the ground. Alrighty, guys, so to find that coefficient of static friction, we already found it to be 10.6. The weight's 19.6. Divide the two. That's all you got to do. It's a ratio. Okay? The normal force is the same as the weight if you're on a flat level surface. It's perpendicular to the surface. That's why it's called the normal force. Oh, and we're calling this the stickiness. It's not really friction force. That's our friction force. That's a force. But this is we're going to call a ratio of forces. Newtons cancel out. There aren't any units. Newton divided by Newton is nothing. So it's a coefficient, but it's describing what the stickiness is like. All right. So when you do the static coefficient, it's always the maximum static friction force that we're talking about. You can have a situation where you're not using your maximum, but when you calculate the static, that's with the maximum static friction force. Okay, so it's just your 10.6 divided by 19.6. So remember, we're using the maximum force can be applied just as it starts to budge. Alrighty. Well, we got a 2 kilogram block. It's a different kind of block called a brick, and it's 19 points up, 19.6 down. This is a new scenario, it looks like, so we're probably going to have a different friction force altogether. Just to start it in motion, it takes 11.8, guys, just to budge it in motion, okay, without it beginning to move. So anything barely above that, it just barely moves, okay, so that's the most. That's the maximum force that can be applied without it moving. Okay, it's 11.8. 11.9, it starts sliding, and then the friction drops because it's kinetic. So to find the kinetic coefficient, the maximum is 11.8, divided by the 19.6, newtons cancel out, and it's 0.6. You might say 0.6, what does that mean? Well, we'll get to a chart in a moment to make it help give it a little more sense of what, if that's sticky or not sticky, okay? So is that sticky like a cat's tongue, or is that sticky like your foot on ice? What does that really mean about grippiness or stickiness? We'll get to that in a moment. Alrighty, so let's do the kinetic coefficient. Well, there's not a maximum kinetic friction force. It's just what the friction is while it's moving, fast or slow, okay? It could be accelerating and you still have the same value, but if you want to measure the kinetic friction force, you want to move it at a constant speed. So in this case, it looks like the applied force, FA's applied force is 8.8, keeps it moving at a constant speed of 1 meter per second. So that would mean that would be the kinetic friction force as well. Okay, so you apply a force, keep the object moving at a constant velocity, but remember, don't push up, don't push down, push to the same direction as your flat surface. So you always push along the surface perpendicular to the normal. That way you're not increasing or decreasing a normal force by pushing down on it or lifting up on it. Alrighty, there you go, guys. 8.8 divided by the normal force, 19.6, it's going to be less. And in most cases, the kinetic friction coefficient is less than the static because it's less sticky. So it's a smaller number. In some cases, there's really not much of a difference. Okay? It moves right into the kinetic, and the kinetic is about the same amount as the maximum static, but in most cases, the static is a little stickier. Think about if you ever taken something off of a painted shelf. Sometimes it's a little sticky pulling that object off the painted shelf because that's what paint does. It sticks to the wall. If paint didn't stick to the wall, it wouldn't stay on the wall. So paint tends to like a lot of things. So not only does it stick to walls, other things stick to paint as well, even if it's dry. And the longer it sits there, it gets a better grip and harder to break that thing loose. Okay? But the point is there aren't any units, so a number smaller than 0.6, 0.45 is less sticky because there's less force per the same weight. Alrighty. So you notice the static friction forces are greater than the kinetic. Some they're about the same, like here at Teflon on steel. It's only 1 sig fig, but there's not an appreciable difference. But for most things, it's a little bit stickier, or the static is a little bit higher number than the kinetic. Okay, so the highest, grippiest thing on here, well, here's something strange. Glass, 0.94, that's pretty grippy. That means it's almost a coefficient of 1, meaning the friction force is the same as the weight. But the crazy thing is, look at this. This is the opposite of sticky. Look how small that number is. So the moral of the story is, I don't know if you ever played with glass, but if you put one sheet of glass and another sheet of glass, it's hard to push it. They are pretty hard to push. There's a lot of grip. But as soon as you get that glass moving, it starts gliding right on top of the other piece of glass. It's kind of different because most things you don't have that big difference. Okay? So what you guys are used to is a lot of grip like rubber tire and concrete. Well, that's why your shoes are made of rubber, guys. On the bottom, you have rubber soles. Some people have leather on the fancy shoes, not as grippy. So sometimes they'll put some rubber on the bottom of that heel on your shoe because rubber tends to be grippier on most surfaces than a lot of things. Okay? And you get it wet, you get that the road wet, it's less grippy or less sticky. So now if your tires are skidding or trying to screech, you actually get a little less grip, and especially if it's wet. So stopping distances are longer when the surface is wet than they are when the surface is dry. Those are things you got to consider when you're driving in a wet surface, or even on snow. I know they don't have rubber on snow, but if there were snow, it's even less than that. And here's steel on ice. That's a pretty low coefficient right over there. It means there's not a lot of grip whatsoever, especially once you get moving. You get a teeny bit of grip when you're not moving, but even half of that grippiness if you're already sliding. Okay. Notice he said on wet snow. I don't know if you've been skiing much, but wet snow can be kind of grippy. It's not always the most fun to ski on because you just can't get up to the same kind of speed that you can on things that's not a wet snow. You get a drier snow or a colder snow, you could actually have less grip than that, and you really start flying down the mountain, or however you're skiing. So Teflon on steel. So what do you mean? So Teflon, you have that on some of your cooking pans. They put a Teflon coating on there because a lot of food doesn't stick. You don't need a lot of oil on there. Food just is not attracted to the Teflon. So you might think, well, how did they get Teflon to stick to the steel pan then if it's not very grippy? Here's the crazy thing about Teflon. It's smooth on one side the way they make it, but it's got these dangly molecules on the bottom. And these dangly molecules can grip around some of these steel molecules on the pan, but it's the other side that's not very grippy on the things. So they use Teflon on some ball bearings, which they don't have to use a lot of oil, makes it low friction. So they use Teflon on a lot of things. So back in the day when I was growing up, they had these bullets called cop killers. And the reason they called them cop killers is they have these new Kevlar vests that came out when I was your age. And what Kevlar is, they're very tight fibers, so tight that a bullet hits those fibers and it can't squish all the way through. It makes a nice dent in your body and everything, and it hurts like crazy when you get shot, but it can't penetrate into your body because it can't get through the fibers. Well, these cop killer bullets were covered in Teflon. Teflon is less friction. The Teflon coated bullet could actually squeeze through those fibers and go right on through. So since that time period, they have body armor, which is not just Kevlar anymore. They actually have steel plates inside the vest. And so if you had that kind of a bullet, Teflon is still not going to penetrate the steel plates, probably, depending on what kind of bullet it is and the speed of it and so on. So Teflon makes things less sticky. Okay? And there you go. So these are experiments that people have already done. This is the experiment that you're going to do on Monday, is you're going to look at both the static coefficient of friction and kinetic coefficient of friction for different surfaces and see how mass affects that. Okay, well, let's keep on rolling here. In fact, we might do another little pause. Yeah, we're going to do another little pause before we actually calculate. Learn how you could go back and use that coefficient to calculate friction. That'll be your part 3 video.